Hey everyone, this video is going to show you how to algebraically determine the y-intercepts, the x-intercepts, the domain, the range, the axis of symmetry, the vertex, and the maximum and minimum points of a quadratic function. The first one we're going to start with is y equals x squared minus 5x minus 14. First, what we want to look for is the x-intercepts. How we algebraically determine the x-intercepts is that we need to have this in factored form. So we need to factor the quadratic. So what we need is two numbers that multiply to negative 14, and they add to negative 5. The two numbers that are going to satisfy this equation are negative 7 and 2. Because this is a quadratic where the a value is equal to 1, we can jump right to our factors, and we'll have y equals x minus 7 and x plus 2. Here, what we can look at then is what would have this equal to 0. We're looking at what factors, or I guess what numbers for x would make each factor equal to 0. So what we can do here is set each factor equal to 0 separately, and then we will solve each of these equations. So the first one will add 7 to both sides, so we get x equals 7. The second one will subtract 2 from both sides, and we get x equals negative 2. So my x values will be at 7 and negative 2. Next, let's look at the y-intercept. The y-intercept is really easy to identify if you have it in standard form. It's always just going to be equal to the constant value. The reason this is happening is that when we're looking for y-intercepts, this is happening when x is equal to 0. So when I input 0 into my equation, I get 0 squared minus 5 times 0 minus 14. Anything times 0 is 0, and so these kind of just become negligible, and we just get y equals negative 14. So that's my y-intercept. Just to give us a nice little visual here, I'm going to draw a picture of kind of what this would look like if we had it on a Cartesian plane. So I'd have my x-axis and y-axis here, x-axis and y-axis. If I was to then identify my x-intercepts, we would have an x-intercept at negative 2 and at positive 7. And I'll have a y-intercept at negative 14. Like this. And that's what we have so far. Next, let's look at the axis of symmetry. The axis of symmetry is always going to be halfway between the x-intercepts or any 2 points with the same y value. So what we can do here is just find the average of the two numbers that we've been given for the x-intercept. So to find the average, we're going to add those together and then divide by 2. So we'll have 5 halves. We could always bring that down to 2.5. I like to usually state the axis of symmetry as an equation, so x equals 2.5. Putting that into our drawing, it's going to be a vertical line that crosses through at x equals 2.5. So about here, which makes sense. This is cutting those x-intercepts right in half that distance, and then we have our line. Next, let's find the vertex. Well, what we know about the vertex of a quadratic function is that its x value will always be on the axis of symmetry, which we already have. So then how we find the y value is we can substitute the x value in. So what we're going to do is we're going to have y equals, and instead of x, we're going to replace x with 2.5. So when we do that, we're going to have 2.5 squared minus 5 times 2.5 minus 14. Let's plug that into a calculator to determine how to do this. Or again, if you need to do it by hand, you can do so as well. What you should get here is negative 20.25. So putting this all together, the vertex is then at 2.5 because that's the value for my axis of symmetry, and the y value is negative 20.25. Let's plot that point. So we already have 2.5 labeled from our axis of symmetry, and then we're going to go down to about 20, just kind of estimating here, and we've got a point like this. And what we can see is we've kind of already got that quadratic shape, right? If I connect all the dots with a nice curve, we're going to get a quadratic. Next, let's identify the max or minimum point. Well, we can already see that this quadratic is going to open up. If I just draw a line in to connect all my dots, here's roughly what I have. And this is a quadratic that clearly opens up. So it's going to have a minimum point. We already have the y value of the vertex because that's what we just solved. So we already know this answer. The minimum is at negative 20.25. Domain and range. For domain on any quadratic function, if you're just graphing it, there's no other restrictions like in word problems. The domain is always going to remain the same. So it's going to be for all values of x such that x is an element of the real numbers. And then for range, what we'll have is for all values of y such that, and here our range will always have some type of restriction because we have a vertex. It either is going to turn at some point, whether it's opening up or opening down, and so there will always be a restriction. Here, what's important is to look at the y value of your vertex. Here, the lowest point that it ever gets to is negative 20.25, and then it turns around. So we can't go below that number. So what that means is that y always has to be a number that is greater than or equal to negative 20.25. And y is an element of the real numbers. And then we have our range. Let's try our second example. This example is written in factored form. So first, let's find the x-intercepts. What's nice about factored form is that we can easily find the x-intercepts from our factors. We're going to take each factor and we're going to set that equal to 0 separately. And then we'll solve both of these equations. For the first one, we'll add 1 to both sides and we'll get x equals 1. For the second one, we'll subtract 2 from both sides and we get x equals negative 2. So our x-intercepts are at 1 and negative 2. How do we find the y-intercept? It's very similar. Remember that y-intercepts happen when x is equal to 0. So all we need to do is plug in 0 into our equation and solve for y. So y will equal negative 2. We'll have 0 minus 1 times 0 plus 2. Simplifying this a bit, we've got negative 2 times negative 1 times positive 2. So what we're going to get here is negative 4. Oh, excuse me, sorry, positive 4. Because negative times a negative is positive. Next thing that we want to look at is then solving for the axis of symmetry. The axis of symmetry is going to be done the exact same way as we did the previous one. It's going to be halfway between our x-intercepts. So what we're going to do is take the sum of those two numbers and divide by 2. What we're going to get here for the axis of symmetry is we're going to get negative 1/2 or negative 0.5. And again, I'm going to put x equals just so I can state it as an equation. So we get x equals negative 0.5. Let's stop here for a second and draw a picture of what this should look like. So we have an x and y axis. We have points at positive 1 for the x-intercept and at negative 2. We have a y-intercept at positive 4. And we have an axis of symmetry at negative 1/2. Perfect. It's starting to look like a quadratic. If we had to guess where the vertex will be, I would guess it's going to be somewhere just above 4, and then it's going to turn around and go back down to that other x-intercept. So let's algebraically find that. It's going to happen the exact same way as the previous question. We already know the x value of the vertex. We need to plug that into the equation and solve for y. So when we plug in negative 0.5, here's what it's going to look like. We can clean this up a bit. We can go negative 2 times negative 1.5 times positive 1.5. And what we're going to get here for our y value is positive 4.5. So we're going to have a vertex at negative 1/2 and 4.5. We kind of have a lot of information here. We could probably now draw in our quadratic or curve. And now it's making a parabola shape. So there we go. That's kind of what it would roughly look like if you were to put this into some piece of graphing technology. The vertex is then at negative 0.5 and 4.5. Looking at the maximum or minimum point, because this graph opens down, we're going to be having a maximum. And it's going to be equal to the y value of the vertex, which we know is already 4.5. So we have a maximum at 4.5. Same thing with, like I said, with the domain. We're never going to have a restricted domain with a quadratic, unless it's some type of word problem or something else is kind of going on. But with a basic quadratic, domain will always be the same. For range, we will always have a restriction. So for all values of y such that, and now we need to input our inequality. all of the y values have to be smaller or less than 4.5. So we're going to say y has to be less than or equal to 4.5, and y is an element of the real numbers. Let me know if you need any help on trying to solve algebraically any of these things with quadratics. Thanks.